Rasters are structured as a regular grid of cells. Now, where the primitive for vector data are points, the primitive for raster data are cells arranged in columns and rows that create a regularized grid of data. And that grid of cells includes a coordinate system, a reference coordinate, cell size, counts of rows and columns, list of cell values as integers or real numbers. The thing I really love about raster structure is it is very, very simple. Again, it's just cells arranged in rows and columns in which the upper left-hand corner is referenced on a coordinate system and the cell size is defined along with the number of rows and columns. You can see the layer properties in ArcGIS by right-clicking, for example, a raster dataset like a TIFF image, and then going to the source in the layer properties window. And there you can see all of the information I'm describing on the left in the window on the right. So it's the number of columns and rows, it's the size of each cell. In this case, it's 30 by 30. What else is in here? The pixel type and depth describes the type of data that is stored in this raster data set, and including the projected coordinate system there you can see at the bottom. So raster cell size is important to consider when you are utilizing this data structure to model your world. The height and width of a single cell can really affect the resolution of your data. And in the image on the left, you can see the same feature, this kind of kidney bean shaped pond, we'll say, mapped at different resolution or cell sizes, 1 meter cells, 2 meter cells, or 4 meter cells. And when you map this feature at different sizes, you can see that the overlying raster data looks different. In the 1 meter cell, I can really make out what the kidney shaped bean looks like, but in the 4 meter cells, it doesn't. It looks kind of like a reverse F, for example. So there are advantages and disadvantages to choosing the height and width of your cells. So you have to be really thoughtful when you're doing this and make sure it supports whatever your purpose or application is. If it's higher resolution data, you'll get a smaller cell size that has a higher feature spatial accuracy, but there'll be a penalty. It'll be slower to display and process because of the really large file sizes. If it is a lower resolution data set, you don't have as good a spatial accuracy, but the display and processing is much faster and the file size is much smaller. If you look on the right-hand side of your screen, you can see two images that show the exact same extent for Austin Bergstrom International Airport. And you can see there's a 3 meter higher resolution image and a 10 meter lower resolution image. And so depending on what your application would drive which image you might choose. If I wanted to identify, for example, individual airplanes, then I would need to use the 3 meter because I need several pixels to construct an airplane that's visible in the imagery. But if I was just interested in identifying where, for example, developed and undeveloped land is, then the 10 meter lower resolution image would work better. Raster data not only includes geometry, but you can store values in it as well. Those values are stored as floating point or integer values. Floating point are decimal numbers. Integer are whole numbers. So floating point is really good at representing continuous features that fall along a range, for example, like population density or temperature. Integer is better at representing discrete features or phenomena. So like land cover, it's water or forest or grassland. It's not on a range of things, it's just one or the other. For floating point data, the geometry and values are stored together in a list of values. You can't actually open a floating point attribute table in GIS. But for integer data, the geometry and values are stored separately in a table. And so you can open the attribute table associated with an integer raster. If you look on the right-hand side of your screen, you can see the different bit depths and how they affect the amount of data that you can store in there. So 1 bit is really just binary data. It either is 0 or 1. It either is or isn't whatever you're interested in, all the way down to unsigned 64-bit, which you can store really large whole numbers in. And so which approach you take depends on what the data is you're ultimately capturing. And you wouldn't want to use, for example, unsigned 64-bit to store a binary data set because you'd have this unnecessarily huge data set that really slows down visualization and processing when you don't really need to store that big of numbers. So you have to be really thoughtful about ultimately the phenomena that you're modeling and the resolution that you need when you pick the size of your cells, but also the way you're going to store the values in your cells.